good to go? Okay. All right. Well, thanks for Ascend for inviting Rez to come have a chance to come talk to you guys. What I'm going to talk to you guys about today is a case study on how we took how we looked at how we could integrate battery energy storage into a vertically integrated utility as their own balancing authority to enhance their operations and defer the need for additional generation for peaking needs. The reason I have Ray, this is Ray Duthu up here, Rez and Ascend partnered on this, and we'll show you a little bit what that structure looked like in just a few slides. So we'll go ahead and get started. So before we get into the case study, I just wanted, for many of you know who Rez is. We've worked with many of the utilities and other entities in this room. But for those who don't know, Rez is a EPC company. First and foremost, we build and develop and construct wind farms. So globally, we have over 10 gigawatts of wind farm experience. We do a little bit of solar, a little bit of transmission, and then my focus is in energy storage development and construction. We currently have in development, under contract or under construction, 240 megawatts, nearly 300 megawatt hours of energy storage globally. So we're a construction company, but we're not really a consulting company, but what we do want to do is make sure that the energy storage industry as a whole moves forward. So that's why we find ourselves participating in more of a consulting type environment as I'm going to present to you now. So I kind of want to just lay the groundwork a little bit. So really, where has energy storage really taken off lately? And that's mostly in Hawaii and California, and that's due to some pretty obvious reasons: really high PV penetration, opportunities for shifting PV energy from daytime to nighttime, peaking capacity needs. I'm sure you all are aware of Aliso Canyon. That created emergency RFPs for very large 4-hour duration energy storage systems in California. Not to mention AB 2514, which is a mandate in California. So most of the big storage platforms are being put there, and it's been really easy to justify those storage assets due to those reasons. So the utility that we worked with is not in California. They're a vertically integrated utility. They own all their own generation. They do all their own balancing, and they don't have a whole lot of exposure to storage. So what we did is we looked at them and we said, okay, what's the low-hanging fruit for energy storage? What is energy storage really good at doing based on what we've seen elsewhere, such as PJM, and that's frequency regulation. But what's not listed on here, and what should be, is the utility originally came to Rez and said they applied for a 200 megawatt gas peaker plant, and the PUC basically rejected it and asked them to do their due diligence and look at alternative energy solutions. So basically, we partnered with Ascend to say, how can we use batteries to defer the need for that peaker plant, but also have a net positive cost benefit. So here, real quick, is the study approach and methodology that we took. So starting on the very left-hand side, we split it into two different sections. So not only did we want to look at how can we defer the need for this peaker plant through ancillaries and direct peak shaving, we also looked at distribution analysis. So we also provided the siting for them. So we looked at 10 to 15 different distribution-sited circuits and said, okay, what other benefits can we collect from these circuits? Maybe we can get some power quality benefits. Maybe we can get some outage mitigation service or some T&D deferral. So we looked at those, and that was Rez's primary focus in the study. Where we brought in Ascend was the bulk generation analysis down there at the bottom through their production modeling software. So how can we use batteries and dispatch them in their system such that it optimizes the dispatch of their traditional existing fleet of generation? So that And we'll show later we probably found that to be most effective through frequency regulation and a little bit of energy arbitrage. So the next step of the process is basically marrying those two. So how do we co-optimize those benefits that we found in the distribution analysis and the bulk generation analysis? And then an output, give recommended size locations, applications, commercial operation states, cost-benefit stacks, and the detailed revenue requirements and avoided costs. And Ray, if you want to...
Yeah, I'd be happy to. So I just want to chime in for a little bit and talk about how we use the SINS PowerSim tool to set up the bulk generation analysis, how this fit in to this project. I'm sure many of you have seen or used PowerSim before. What we did was we built, I think, just the most simple approach we could take. We had the entire model of the utility, generators, loads, regulation, transmission. We built all of that out as is and ran it at a very high level of optimality, which might sound a bit strange to say a high level of optimality, but a very nearly optimal solution, as close as we could get using the linear solvers. And then we did the same thing, but we put a battery in there. And so by doing this, we can look at, this was case A, no change, and in certain, let's say, key years we identified, we had this sort of net revenue for this utility. We put in a battery, and we let the battery offer load, move load as it needed to, or offer regulation as it needed to. Totally free just to do what the battery needed to do to make the entire solution even more optimal, even improved. And we could look at net revenue 1, net revenue 2, and say the battery, just the addition of this battery of different sizes, different durations, led us from A to B. And so that's the way we set up in the Ascend model. I'm going to go over that for the next few slides. You can keep the clicker. That's fine.
Okay. Sure.
So, yeah. So, what was part of the rationale for this? This utility is drastically increasing their solar penetration over the next 22 years. About 300% of what it is now. And I think if we've been at this talk for a few of these different presentations, we'll know, this is a new concern. This is a rising concern for a lot of utilities. We increase our solar penetration, and now a lot of our other needs have also increased. We need more transmission or more storage, some way to deal with the uncertainty that solar creates. We just have a simple plot over here for the percent increase in the PV penetration over time. On this end, this is kind of where the rubber meets the road a little bit more. These are our key years, 2017, 2027, 2031. Here's the average regulation up requirements, just the average hourly requirements, factor in the solar projection. So 2017, 165. As we go into these later years, and I guess I'm sorry, it was also 2020. These years are different. These are the key years. We just must not have updated the title. And we can see the nighttime requirements, not a significant increase. 65, 69, 76, 84. This is 23 years later, 22 years later. But the daytime requirements, when the solar is having an impact, we went from 100, 123, 137, 150, over a 50% increase in regulation requirements. Mm-hmm. So this is really the opportunity for the battery to step in and smooth out some of this sort of upcoming problem.
Yeah.
Next slide.
I just wanted to add one thing. So your regulation requirements are typically determined by your inertial stability in the system. So in the daytime, there's a large increase in regulation requirements. That's because of the large increase in solar penetration, though. At nighttime, you see a fairly slow increase in a much lower number, and that's because at this particular footprint of the utility, they don't have a whole lot of wind. So at night, the load is fairly stable, and there's not a lot of variable generation to throw that off. So keeping that regulation number down.
Sure. And this is just highlighting a SINS regulation tool. So this is using a minutely analysis of the the load and the solar regulation, all of these factors coming in, seeing the impact. We can see the sawtooth inter-hour volatility created by the solar. So this is how we determined the slide previous, those average regulation requirements each year during day or night. This is the tool that we use to set that up. Let's just go to the next slide. Okay, so these are a little bit out of order, I apologize, but we have some the benefits. We have three key components to the benefits for batteries. And the first one is avoided fuel cost from the batteries providing regulation services. So the idea here is, let's say in case A, when I had no battery, I had to offer regulation, and the best way for me to solve it at the time was to take this coal plant and run it here. So I had some regulation up capacity. My heat rate is all the way above 11,000 now on this coal plant. When I go to case 2 and I place a battery in, and that battery, let's say, is well enough sized and placed that it can offer the regulation, I have it at a good state of charge, I can now take my coal plant, run it all the way at maximum. Why not? I have that freedom. Now my heat rate is below 11,000. And this is where we saw, when this is a utility that has requirements for load, requirements for regulation, this is where we saw the real benefit for batteries. You know, when it's not just buying and selling and prices, but when you have actual constraints, we saw these kind of benefits. And these points up here just sort of highlight that. We have more efficient operations of the thermal generation. And occasionally, the real high ticket value, if you have a high startup cost on some of your CTs, you might be able to skip some of those because the battery is there to take over, let's say, the worst case scenarios for regulation. Let's go to the next slide. So another, number 2, please excuse the 3.
There's 3 total.
There's 3 total.
In no particular order.
Yeah. Certainly not in my favorite order, apparently. Battery can offer fast-acting response to regulation signals, which offset a disproportionate amount of regulation from traditional resources. And so the point, what we're watching for here is overshoot. We have, if this is our signal to serve, this blue line, perhaps our actual operations look more like this orange line. Because we have limitations with thermal generators. One of my first jobs was turning power plants into video games. I built the simulators that they train the control board operators on. And I can tell you from experience, there's not just a knob you turn and it goes from 10 to 20. It goes from 10 to 21 to 19, 20 and a half, 19 and a half, 20. So, we have this all the way down, I think, in each generator's level. We have these limitations where we can't perfectly meet the required signal. But a battery can. A battery has nearly instantaneous ramp, and it has a very fine control on exactly what it can do and can't do. So another study that we looked at from another utility actually came up with some capacity equivalents of energy storage furnishing frequency regulation. So if we were to put a battery into our regulation up requirement, it's worth a disproportionate amount more than its size. So if I put a 10 megawatt battery in, it has a multiplier of 2.6 in this case. It's worth 26 megawatts of regulation because it can operate more quickly, target the signal more accurately. I don't need all 26 megawatts. I just needed that 10. Now, and that is also a case, I don't have the plot there of that. This is a case of diminishing returns. So if I have 100 megawatts of regulation, I put a 10 megawatt battery and I get a very good multiplier. If I have 100 megawatts of regulation, I put a 100 megawatt battery in, I don't get as good of a multiplier.
Yeah, so what Ray is saying, get the 2.6 times capacity equivalence if you have a 100 megawatt up requirement, but if you max that out at 50 megawatts, it's a much smaller benefit. So there's diminishing returns.
A better way might have been to put that if I have a 10 megawatt battery and 100 megawatt requirement, or a 10 megawatt battery and a 10 megawatt requirement. It might have been a better way to put it. It's not the size of the battery per se, it's the size of the battery in relation to the requirement. Mm-hmm. So it's a little bit gets you a big gain right off, and then as you add more battery, you get diminishing returns.
Yeah. And another thing to observe here is as you go into the future, you have increased renewable energy penetration, so that value of that relative battery size will go up.
Yeah, in this case, the battery remained 10 megawatts for the entire study, but the regulation up requirements increased as we went along, so the multiplier increased over time for the battery.
Mm-hmm. And just another thing to mention, this is a very similar characteristic exhibited in PJM. Many of you may have read the PJM KEMA Kermit report that had similar findings as this. While Ray's
just receiving some notes. I'm fine.
Oh.
The sort of last item I want to close in on is the ability to hedge against price spikes or perform some amount of load shifting. So obviously, the battery can offer regulation. It also might charge or discharge to shift load to avoid high price spikes or take advantage of price spikes if we're in an opportunity where we could sell to another utility. Now, I should have backed up a little bit, and I apologize for that, but I did set some rules up on the way this battery operates. One of the most primary is it can either, every hour, it could either do regulation or it could load shift. It can't do both. So this is really a yes/no. This is a binary choice for the battery in these different hours. And so that, I think that gives us a little bit, when we look at this chart, a little bit idea of what it did do. Now, we've got 4 battery sizes here. This is, if it's hard to see, this is a half-hour duration battery. This is a 30-minute battery. This is an hour battery. And, you know, 10 megawatt, 25 megawatt, 50 megawatt, 100 megawatt battery. Now, it seems, you know, pretty linear. The battery gets bigger, we get more value. But this is a 10 megawatt, this is a 100 megawatt battery. This is not 10 times this. Right. So we didn't get a one-to-one linear increase of value with battery size. The 10 megawatt battery was able to cover all of the worst regulation choices. When we desperately needed 10 more megawatts of regulation, we had to start up a CT to do it. Or we had to run a coal plant at some level we would hate to. The 10 megawatt battery covered all those really bad cases that crop up over the year right off. The 100 megawatt battery could too, but it also covered some other cases that maybe were not quite as bad. I mean, it's still better that we had the battery, but not quite as big of a deal that we had the battery. So we got a lot of value up front just at taking care of the worst avoided cost situations with a smaller battery. Now, they did also do some energy shifting, and that's another reason why the 100 megawatt battery is worth more than the 10. But the regulation was really worth much more in this case, being able to cover those avoided cost situations. So that's kind of my takeaway I have here. Another case, yeah, we have it up here. You know, this is over time for each one of these batteries. So you can see over time, as load increased, as regulation increased, the battery became more and more valuable. This is something that grew in value over time.
Yeah, and one other thing that this shows you, to his point on energy shifting between the half-hour battery and the 1-hour battery, you barely see an increase in between the two. So that shows that you're not getting a whole lot of value of shifting a large amount of energy in this particular region.
Yeah,
these results will be totally different depending on what region you are in the country. But in this particular region, they don't exhibit a need for a lot of energy shifting. And it's due to a lack of significant PV penetration compared to areas like California.
Yeah, that's a very good point. Thank you for bringing it up. I mean, that's even more clear evidence from a half an hour to an hour, because this was an hourly time step. So in terms of operational decisions, really you're talking about the hour battery is twice the size of the half-hour battery in terms of energy. So if it was going to load shift, it could load shift twice as much. And we do not even see close to twice the value with the hour battery.
It's going to be twice as expensive.
It would be twice the cost. I think Peter already covered it, but a lot of this depends on the flexibility and the cost of the surrounding assets. I guess if I imagine that if I was a utility and had all hydro, then maybe this battery wouldn't be worth as much. Because I would already have very high low-cost flexibility. But if I'm a utility and I have a lot of base load and some CTs, then I think this could really start to create some value. With that, I want to hand it back off to Peter.
Cool, thank you. So if you remember the original methodology graph that I showed you, so we just kind of covered the bulk generation analysis portion. We're not really going to cover the distribution side. I'll tell you why in a second. But right now I'm going to talk to you about marrying the two of those. So we did the distribution analysis and the bulk generation analysis. So now it's time to basically combine those two benefits and do the financial analysis part. And this is kind of an example of one of the systems that we looked at. So some of the key takeaways are that capacity and frequency regulation value represents the bulk of the benefit. So if you're not clear on how we're getting capacity value, remember this graph. So this is a capacity equivalence. So this 10 megawatt storage asset is basically freeing up 26 megawatts of thermal generation to go do something else other than frequency regulation. Typically, we want it to do a longer duration service, especially if it's a coal plant. So that's actually capacity value that was created. So we're able to capture that depending on the, I'm going the wrong way. Depending on the system size. Sorry about that. So on the green here, you see the benefit that's related to, I call it frequency regulation, but that's really the production cost efficiency modeling that you get, the operation efficiency that you get from the production cost modeling through frequency regulation and energy arbitrage. But a significant amount of that value is from, in the orange, that's that offset generation that is able to do longer duration services. So those traditional thermal assets were liberated to perform longer duration services. And yeah, we looked at some distribution deferral. Now this is, you can probably imagine this is probably a pretty small system, a distribution-sided system, due to the cost of it. But the distribution deferral portion of it is really just a sliver of the benefit. And what we found, this is a pretty consistent theme. I've been at RES for a couple of years, digging and digging, looking for distribution deferral opportunities, and they're few and far between. They do exist, but in most, 95% of the time, you can't justify an energy storage system at today's cost just on a T&D deferral or a distribution deferral application. So another thing I wanted to point out here was so if you see the purple up here and the green, so the purple, so the stack before the purple is for a 15-year project life. And the blue and the maroon here is for a 15-year project, the cost of a system. So that's warranties, maintenance, so O&M, and CapEx for that system for 15 years. So what if we wanted to extend the life for another 5 years? How much more value would we get? We would get a significant amount more value based on that capacity value and ancillary service value, right? And at what cost? It's really just additional operating costs. So maybe it's a little bit more augmentation of the batteries, capacity maintenance, that kind of thing. So it's really just slightly more operating costs, but you get that much more value. So the point I want to get here is battery systems can last for 20 years, and they can provide significant more value if you design them to do so. So we already talked about this, distribution not highly valued, longer lifetime projects. Okay, we'll move on. So what I wanted to show you guys a little bit of a nuance that we kind of discovered while working on this. Now, what you see here is a load correlation of the distribution load. So that's the feeder load on the y-axis and the system load. And I have the lines of feeder load over 90th percentile and system load over 97th percentile to say, okay, this is when both of the systems are peaking at the same time. So if you move to the right, and I think the terminology is a little bit confusing, but so that black square there is when you're to the right of the system load and above the green line. So what that means is the system, so the feeder is peaking most of the time when the system is peaking. So that means is you can, sorry, I need to articulate this a little bit better. So that means, so your feeder load is peaking at the same time as your system load. So if you imagine you're trying to perform frequency regulation on a distribution circuit, you have a transformer that's sitting in your way, right? So if your system is peaking, you can't really charge the battery anymore because you already reached your max capacity on your distribution circuit. So you can't basically regulate down at all. So what that means is you have to take the battery out of the frequency regulation service. And what did we learn before? We're creating all this capacity value by the battery performing frequency regulation, allowing those thermal assets to go ahead and perform those long duration peaking capacity services. So basically, this relationship is at odds with this whole concept. So the whole point is distribution-sided systems have a lot of challenges when trying to capture these bulk benefits. So what you really want to see if you want a distribution-sided system is the inverse of this. You want most of your data points to be actually below this green line. So when the distribution system is not peaking at the same time as your system load. So moral of the story is it's really hard to do distribution-sided energy storage systems. So I guess the point here is, so if you're peaking at the same time and you want the battery to perform a capacity service, it can't do the frequency regulation anymore. So the only thing it can do at that point, if you want to use it for capacity, is discharge it over that 4-hour period. So that's if you have a half-hour battery, that's a pretty short time that it's discharging for. If you want the 10 megawatt, 5 megawatt hour system, really a fraction of that 5 megawatt hours it can discharge for over 4 hours. So it's quite diminishing. So if you're off peak, only at these times can you actually capture that capacity equivalence that we were talking about. All right, so the conclusion here is using batteries to furnish frequency regulation opens up the door to achieve capacity credits from existing generation that you already have. So you don't have to build new generation to be able to more efficiently utilize your existing fleet. And it really makes it easier to rate base. You get renewable energy integration benefits, capacity credit creation, fleet dispatch optimization, and all the environmental benefits that we haven't talked about at all yet. And I think what we just learned is that there's little value to begin with on distribution-sided systems, and then there's further complications when you're actually trying to capture those bulk benefits, depending on the dynamic of the peak load with the distribution load. So at the end of the day, what we did is we recommended a portfolio for the utility. Thank you. And that consisted of 8 to 10, can't remember the exact number, different specifically cited distribution-sided systems. Actually, it was a combination of transmission and distribution-sided system. To get a picture like this, we needed something like this. This is a transmission-sided system that doesn't have any of those load restrictions that the distribution-sided systems do. Basically, we recommended a portfolio and also CODs for all of them. And this was kind of the result, what we estimated their total MPV would be for that entire fleet based on distribution benefits and the production cost, or the value that Ascend showed us. So this is an interesting chart. So we also wanted to show them how this could potentially fit into their IRP. So this is an example load balance sheet, quite simplified, so we can paint the picture. So if this is their peak demand forecast, and if you imagine the green, so the green is what the load balance sheet would look like without any energy storage, right? So they're existing planned resources, and let's say that didn't change over the next 20 years. That's not realistic, but just imagine that. And they'll have a usual import transmission with some contingency built in, so maybe they have another 470 megawatts. And then you need to plan for a little bit of contingency. Usually that's based off your largest generation asset tripping offline. And so if you look in this green region right here, basically shows so your total reserves after subtracting out your peak load from your existing generation and usable transmission. And then if you subtract out your single contingency number here, you end up with your NERC compliance reserve after a single contingency. So if you go below 0, that's when you know you need more generation. So before adding that storage, they would need some new generation to handle their peaks by 2023. Now, if you go back up here, now if you remember, we said a storage asset can be worth as twice as much as a great capacity it can be twice as effective as a thermal asset at performing frequency regulation. So in this case, that liberated 100 megawatts of thermal assets to go perform peaking capacity services. So this was the projection across the whole 20 years. So your new load balance shows that you actually wouldn't need that additional generation for another 6 years. So that's quite a bit of value. So that's all we have prepared. Anybody has any
questions?
When you were looking at the value of the battery over time, it was a couple slides back. What all were you varying? Was it just the pricing, or were you increasing?
Oh, that's a good question. I think it was back to the big chart.
The bar graph?
The bar graph, yeah. Yeah, so in those years, a few things were changing. The load was increasing. The prices were, in general, increasing. And the regulation requirements were increasing. But to maintain a little bit of uniformity between the years, the shapes of a lot of these things were roughly the same. I think they're the same, but it was just an increase, a sort of proportional increase on all these things. There was also increased solar. Yeah.
Peter, you mentioned the siting was a challenge because the feeder in the system were correlated with the heat.
Yeah.
So, did that limit the value that the battery could offer for frequency regulation because it had to provide capacity?
Yeah, exactly. I mean, it's so at this top region here, that means your feeder load is peaking. It can't regulate, it can't charge anymore, right? Because then you're going to overload the transformer at the distribution site. So you either can only regulate up, or you have to take it out of frequency regulation market altogether. So you can't do frequency regulation. You can't optimize the dispatch operation of your system. And then the only thing you can really do with it is maybe use it as a spinning reserve asset and dispatch it over a 4-hour period, which, if you remember on the bar graphs, we said half-hour battery, more or less, is probably the most optimal size for capturing the value of the frequency reg. So pretty short duration of dispatch.
Well, if you're at a system peak, wouldn't you expect to need reg up at that time? Or are you assuming that it's not like a ramping situation, it's just a high?
Yeah, I mean, that's a good question. I'll let Ray jump in, but I think even if you're peaking, you're still going to need intermittent needs, so that's up and down.
Okay.
There's still going to be variability during your peaks of PV generation.
Yeah, the regulation did include up and down, if that wasn't clear, I'm sorry.
Yeah. So what we assumed in this analysis, though, is we just pulled it out of frequency reg market during above the 90th percentile feeder load conditions.
And I guess I'll throw out just additionally, there were actually also in the portfolio spinning and non-spinning reserve requirements, but the battery was offering regulation. So that there were still some requirements that the thermal plants had to serve. Let me put it that way.
Yep.
In this case.
A couple quick questions on assumed assumptions behind these studies. One is, are existing tariffs in place to collect these revenues?
Existing tariffs. Well,
So this is not, the load is the same with and without the battery. So the revenues from the tariffs from the customers, from the users, would be the same. This is reduction in cost, really, more than it would be, or perhaps increase in sales to other utilities, but it wouldn't be, increase in consumer use.
Okay.
That's where the value is deriving from in these comparisons.
And then the second question is, I assume interconnection costs have been factored in?
yeah, so that's a good question. I'd have to look at what we included. Typically, when we do, we might make some, I can't say yes or no whether we included interconnection costs in those stacks. We might have included a certain percentage of the capex or something of the project for interconnection. Let's see here. I think I listed it. I would say, since I don't know, no, we didn't include that. Yeah. Go ahead.
Yeah, since you found the battery benefits were mostly associated with the bulk transmission system benefits like frequency and capacity.
Yep.
Was location then very definitive for the value?
Yes. Yeah, I mean, and that's largely because of this relationship, right? So we did include a few just transmission-connected systems, and we assumed no restrictions on reg up or reg down, needing to take it out of market, all that complication. So that the portfolio mix was maybe 5 distribution-sided circuits and 3 transmission-sided circuits. And then the distribution-sided circuits didn't look like this. They had most of the dots, or at least half, down below that green line, so that they could capture more of that capacity equivalence. Do you have a question?
I wanted to be sure I understood this. Now, is the assumption then that the distribution system is sized exactly right for the
Yeah.
whole system? There was no excess capacity on the distribution system. So if you had a distribution system that had excess capacity, you could still have down reg.
Yeah. So the way that we size these is we sized it so that, because remember I said we're taking the battery out of the top 90th distribution load percentile. So we'll have a PT or something that measures the load. If it gets within above the 90th percentile period, then we're going to take it out, right? So then that way, the way we size the battery is that 90 to 100th percentile difference is how much we could actually regulate. So, for example,
Restricted. Let's say your distribution system wasn't restricted.
only restricted when the load exceeded a certain value. So that restriction is when we.
That restriction was 100% then.
Well, it's only at times when the distribution load is peaking. So one example is we'll just make a really simple example. 10 MVA circuit, right, with a transformer of 10 MVA capacity, and then the load, is most of the time is 90% of the time it's below 8 megawatts. So then we said, okay, at this circuit we can do 2 megawatts all the time except for those times when the load exceeds that 90th percentile. So we'll actually take it out of market during those times. So you can see how complicated it gets.
Yeah.
It's almost, it's a headache for operations, integration, analysis. So in some cases it can be worth it. That's in cases where the peak does not correlate with the system peak. So that's really what the relationship we wanted to look for, was when the distribution peak does not correlate with the system peak. So you don't have to worry about taking it in and out of market all the time. All right. If there's any more questions? Thank you.
Thanks, everyone.
Yeah.